will start how to derive van der Waals equation of state from more fundamental point of view, means how to start from the basic interaction of the among the constituents and how to derive it from a more fundamental point of view or from the first principle of physics. Let me try the how to deduce the equation of state for the real gases using the virial theorem. This is not the rigorous virial theorem as we often encountered in the statistical mechanics. So, here we have started just from the using the simple classical mechanics approach. Now, let me start it. Clausius first did this equation of state for an imperfect or real gas more rigorously using this virial theorem. So, how he had done it, let me start it step by step. So, now let us consider a gas of n identical molecules, each having mass m in a vessel of volume V. So, the total energy E of the system consists of the total kinetic energy plus total potential energy. Total kinetic energy means summed over the kinetic energy of individual molecules plus the interaction energy. Obviously, here we will take simple pairwise interaction, means which depends only on the relative separation between the molecules. Okay. So, total energy of the system is E equal to summed over I equal to 1 to n half m c I square plus phi, where c I is the velocity of the ith molecule and phi is the total potential energy of the system. Anyway, we are not going to deal the any real gas, still we have taken some assumptions closer to ideal gas, slightly deviated from the ideal gas, means in the case of rarefied gas the potential energy is assumed to pairwise additive, that means phi is summed over I less than j u of r I j, where u of r I j is the pair potential between the molecules I and j separated by a distance r I j, which is nothing but the mod of r I minus r j. So, let x I, y I, z I be the Cartesian coordinates of the molecule I, x y z component of the position of the molecule ith molecule, and similarly f of x I, f of y I, f of z I be the components of the force acting on the molecule I. Then we have three separate Newton's law, m d 2 x by d t square equal to f of x I, m d 2 y by d t 2 equal to f y I, m d 2 z I by d t 2 equal to f z I. These are the three Newton's law in three coordinate, x coordinate, y coordinate and z coordinate. So, similarly, the kinetic energy of the ith molecule is m of half of m c I square, which is nothing but the summed over m, because it is the identical molecules, m will come out m x I dot square plus y I dot square plus z I dot square, where x I dot y I dot and z I dot represents the velocity of the molecule in the x y z direction for the ith molecule. Okay. So, using the relation simple identity in differential calculus, half d 2 by d t 2 x I square equal to x I dot square plus x I d 2 d x I by d t square, okay, d 2 x I d t square. Okay. So, if you will use this relation in the kinetic energy equation, so for individual component, means x component kinetic energy is half m x I dot square equal to half times half equal to 4. So, 1/4 m d 2 by d t 2 x I square minus half m d 2 x I by d t 2 x I. Okay. So, 1/4 m d 2 by d t 2 x I dot x I square minus half m d2 d2 xi by dt2 is nothing but the f of xi in. So, half f of xi into xi. So, this is the kinetic energy of the x component. Kinetic energy can be written in this way. Similarly, we can follow the same identity for the y component and z component also, and add them together. What we will get it, half m c I square equal to 1 by 4 m d 2 by dt 2 x I square plus y square plus z I square minus half of f of x I means x component of force into displacement x I in the x direction plus y component of force multiplied by the displacement in the y direction plus z component of the force multiplied by the z component of the displacement. Obviously, this is for repeated indices tells that summation, which is for the ith molecule. So, if you will rewrite in terms of the r coordinate, spherical coordinate, what we can get this 1 by 4 m d 2 dt 2 r I square minus half r I dot f I dot. Okay. So, we now sum this expression over all molecules of the gas and take the average over a sufficiently long time tau. So, thus we get half summed over average over m c I square, that means we are taking the time average equal to 1 by 4 m summation average of d 2 by dt 2 r I square minus half time average of summed over r I f I dot. Okay. Time average has come from the very fundamental fact that the motion of the atoms or molecules in the gas are completely random. They are always under the experience of random force. So, we are interested over a time the value of those quantities over a large time scale. Obviously, that time is always much greater than the collisional time over an asymptotic time scale. So, that gives the concept of time average, because the force each and every molecules or atom always experiencing by random force. So, we have to take some time average of it. Okay. So, finally, where F I is the force acting on the molecule I, which coordinate is r I. So, that is r I dot F I dot. The summation extends over all molecules and the bars represent the time average which starts from 0 to tau. Obviously, that tau is very much larger than the collisional time scale. Okay. So, if you although this is not I do not want to tell this thing in this lecture, but these things if you look for the Langevin dynamics or Fokker-Planck equation, there you will see there are two type of time scale, one time scale which are less than the collisional time scale where random force still exists, another time scale where time is much greater than the collisional time scale. Actually, we are looking for the time average over a very long infinite times, which is known as the steady state system. Okay. So, the first term if you will take the time average, what I will get it, the first term in the right hand side of this equation can be written down as 1 by 4, just you see it 1 by 4 m average of d 2 by dt 2 r I dot square, bar means time average. If you will write down the summation in terms of the integral form of from the definition of obtaining any average quantity is 1 by 4 tau, basically 1 by t, t is the time period, 0 to t f of t dt, that is the general definition of time average. So, same thing applies here also 1 by 4 tau, 1 by 4 is already there. So, 1 by tau m 0 to tau summed over I d 2 dt 2 r I square dt. So, if you will do it, then I can always write down this thing as 1 by 4 m summed over I 1 by tau d2 ddt of r I square 0 to tau. So, this thing has come after doing it by parts. If you will do this integration by parts, then this thing you can get it. So, then if you will put the upper and lower limits of time. So, you will get it 1 by 4 m summed over I 1 by tau 2 r I d r I by dt, because d dt of r I square is 2 r I d r I by dt 0 to tau. Since d r I by dt is nothing but the velocity of a ith molecule, since I told you that each molecule are always experiencing very random force. So, the velocity which is nothing but the d r I by dt, the velocity of the molecule are always fluctuating rapidly, because the velocity arises because of some random force. So, obviously, velocity will fluctuate very irregularly. So, if you will average over for a long time, this velocity you will get the 0. So, that is the reason d r I by dt for a molecule fluctuates irregularly with time, and hence 1 by tau d r I by dt 0 to tau reduces to 0 when tau is very large. So, thus finally, first term is 1 by 4 m d 2 dt 2 r I square average will be the 0. This is because of their force motion is completely random. This is the basic physics behind this average. So, the equation finally reduces to half average of the total kinetic energy, average summed over I m c I square bar means average is nothing but minus half summed over I r I dot f I average, which is let us call say x. So, this is the virial theorem of Clausius, and where x is called the virial of the system. So, what does it mean by virial theorem? The total kinetic energy of all the molecules is nothing but is equal to the x, which is nothing but the virial of the system. Once I will if I will calculate x, then I will get what is the total value of the kinetic energy, average total kinetic energy. Okay. So, according to this theorem, the total kinetic energy of translation of molecules of a gas in the steady state is equal to its virial x, as I have already told you, where x is nothing but the minus half summed over I r I dot f I, and then take its time average. This is nothing but the virial of the system. So, in terms of the mean square velocity c square bar, equation 6 can be rewritten as half n is the total number of molecules, m c square bar. This is the definition of mean square velocity, which is nothing but the half summed over I m c I square, which is nothing but the x. So, each molecule in the gas experiences the restraining force of the container, and also the force exerted by all other molecules in the container. So, each molecule in the gas are experiencing two kinds of force. One is the restraining force of the container, and other force which is exerted by all other remaining molecules in the container. So, virial obviously, since force has two components. So, virial x, virial of the system, can be decomposed into two parts. One part is due to the external force, which is x c, another part is the due to the intermolecular forces. So, x can be written as x equal to x c plus x I. E stands for the external forces, I stand for the intermolecular forces. So, if the pressure, now let me calculate x c and x I separately, then I will add together and then I will get this equation of state. So, what is x c? Okay. if the pressure exerted by the gas is P, then the virial of the external forces like that of an ideal gas is nothing but x c is nothing but the 3 by 2 P v, that is well understood. Second part, on the other hand, the virial of the internal forces is given by x I equal to half summed over I r I dot del phi by del r I average. Okay. How this has come? Let me explain it. As you know, x I is half summed over I r I dot f I intermolecular force, and here intermolecular force is derived by their potential energy. So, f I is nothing but derived by their potential energy, which is the as we have told you, phi is the total potential energy, phi is the total potential energy of the system, and the intermolecular force arises because of the potential energy. So, F is derivable from the potential energy, which is nothing but d phi by d r I bar. R I bar is nothing but the average value, okay, of R I. So, substituting these values of phi and using R I equal to mod of R I minus R j. So, the virial of the internal forces can be rewritten as half summed over I R I dot del u R I j by del R I bar, take its total time average. So, what if you will skip this notation is well understood because of this repeated indices, that half summed over R del d u R by del u R by del R, then take its average. So, I skip the indices which is well understood, which is the repeated indices. So, substituting these values of x I and x e. So, the total x means total virial of the system is, which is 3 by 2 P v, which is nothing but the due to external force, which is just like the ideal gas 3 by 2 P v plus due to the intermolecular force, intermolecular potential, which is half summed over R del u R by del R, and take its time average. So, according to kinetic theory of gases, the mean kinetic energy of translation of a molecule is half m c bar square equal to 3 by 2 k T, that we have already talked about in my earlier lectures, that kinetic energy is a measure of their temperature is a measure of their average values of kinetic energy. So, half m c bar square equal to 3 by 2 k T. Obviously, this kinetic energy only due to their translational motion. Okay. So, then P v equal to n k T minus, then if you will rewrite this equation, that means if you will bring P v in the left hand side, then you will get it P v equal to n k T minus 1/3 summed over R d u R by d R, then take its time average. This is the general form of the equation of state for an imperfect gas, derived from the virial theorem and holds good accurately. So, if you will see it at a first glance, if you will see this, if you will put u, what is u? U is the measure of intermolecular interaction. If in the ideal gas equation of state, we know there are no intermolecular interaction. So, if you will put u of r equal to 0, then it reduces to the ideal equation of state. So, this is the first check up of this equation of state, that we are going in the right direction. So, and if you want to evaluate exactly, then you have to know what is the form of intermolecular interaction. So, if you know the form of intermolecular interaction, then you will plug in the expression, the form of du by dr, then calculate its time average, do all sorts of summation, and finally, you can get the equation of state for the real gases, which is true for in principle it is true, but as we know that its exact evaluation of this equation is not possible, since du by dr is not known precisely. Why it is not known precisely? Because we do not know what is the exact form of intermolecular interaction, because we know a atom is formed by one of the most fundamental interaction, which is nothing but the electrostatic Coulomb interaction. Because suppose let us take hydrogen molecule, hydrogen atom, which is bound because of the electrostatic Coulomb interactions between electron and proton. So, this is well understood, because if you know in quantum mechanics this problem is analytically solvable. But how a molecule is formed by two hydrogen atom H2, exactly you cannot calculate how you cannot calculate how two hydrogen atom form a hydrogen molecule. So, you have to look for some empirical equation of state, because here exactly in principle the formation of molecule should be obtained through the electrostatic or electromagnetic interaction between the all point like electric charges. But since here two atoms are not electrically charged objects, so in principle they are not interacting electromagnetically directly, but they are interacting electromagnetically through in the shielded form, which people used to call Lennard Jones potential or van der Waals force, etc. Here electromagnetic force is there, but which is in the shielded form. In the dipole approximation or quadrupole approximation, you can expand an atom in terms of dipole or quadrupole, then two atoms can interact through the dipole interaction or quadrupole interaction, which is nothing but the shielded form of electromagnetic interaction. So, in principle this equation of state, this is the equation of state for an imperfect gas, but provided if you know U of r exactly, U of r tells you the intermolecular interactions. So, but in general U of r is not known to us. Reason is that U of r is the intermolecular interactions. So, if I know U of r exactly, then I will substitute it there and take its time average, then I can get the equation of state for an imperfect gas. For the ready-made check, you see if you put U of r equal to 0, it immediately reduces to the ideal equation of state. That means, we are going in the right directions, because in the ideal equation of state interactions among the constituents is 0, there are no interactions. So, it gives rise the ideal gas equation of state. But if you want to evaluate exactly this expression which is given in equation 24, this is not possible, because we do not know U of r exactly. The reason is that the reason why we do not know U of r exactly, it has many reasons, because we do not know how the two atoms or two molecules interacting among themselves. Because we know, at least let us take a simple example to clarify this statement. Suppose take a single hydrogen atom, how a hydrogen atom forms, how the bound state of hydrogen atom forms, we know exactly. Reason we know exactly, because hydrogen atom forms due to one of the most fundamental interaction, which is known as the electromagnetic interaction between electron and proton. And if since this interaction is known fully, so it is as we know, although I do not want to tell these things in detail, Schrodinger's equation which tells the eigen energy of this hydrogen atom, which is exactly solvable analytically for this attractive Coulomb interaction between electron and proton. But how the two hydrogen atom forms a hydrogen molecule, that we do not know exactly, analytically we do not know exactly. Reason is that two hydrogen atoms cannot interact fundamentally electrostatic Coulomb attraction. Reason is that atom is not an electric charge particle, atom is not an electric charge particle, but we know that two hydrogen atom interact each other, form a hydrogen molecule. This interaction can be, nowadays it can be explained in terms of the dipole or quadrupole interactions among the two hydrogen atom, and this interaction, this problem is not solved analytically. People used to take that the two atoms are interacting through their dipoles or quadrupole interaction. Sometimes people used to call this is the shielded electromagnetic interactions. So, people used to call van der Waals force is nothing but a shielded electromagnetic force. So, these things are not easily, even for a simplest case, which is the hydrogen atom, which consists of only one electron. If you want to look for the intermolecular interaction having the many multi electron system, so this thing is very complicated thing. However, nowadays people are able to improve a lot using the density functional approach. Anyway, I am not going to digress, I am not going to tell it, because it will be too much digression for this talk. Nowadays, people have developed a new method which is remarkable in the theoretical physics, which is known as the density functional approach, through which people are able to extract the intermolecular form, exact, almost exact form of the intermolecular interactions. If you can extract intermolecular interaction, then in principle you can get a exact form of the equation of state for the real gas. But for the sake of simplicity, for the real gas, for the analytical point of view, it is very hard to get an analytical equation of state for any real gas. So, now let me start it. Let me get some of this, let me extract some of this form of this equation of state for the real gas. So, here I would like to tell you something about the Maxwell-Boltzmann distribution. As you remember, as you might remember in my earlier lectures on Maxwell-Boltzmann distribution of speed, Maxwell-Boltzmann distribution has two kinds of thing. One, it tells how many atoms or molecules having the velocity between v and v plus dv, or it tells the velocity distribution of molecules or energy distribution of molecules, how atoms or molecules are distributed among the in a energy interval between E and E plus dv. This is one Maxwell-Boltzmann distribution law. Another Maxwell-Boltzmann distribution that I have also told you at the end of my lectures of the Maxwell-Boltzmann distribution, there I told you how the molecules are, or atoms or molecules, or in general how the particles are distributed according to their potential energy distribution, which obviously potential energy tells you in the coordinate space. That means, how the particles are distributed in the coordinate space. So, you see there are two kinds of beautiful distribution of the same Maxwell-Boltzmann. One tells the distribution of molecules in the momentum space, in its Fourier space, inverse Fourier space, which is nothing but the coordinate space. It can also tell how the particles are distributed in the coordinate space between r and r plus dr. So, let me exploit that Maxwell-Boltzmann distribution. Okay. So, let me tell a few things more. Maxwell-Boltzmann distribution in the velocity space tells how quickly system will be equilibrated, or how system will achieve thermal equilibrium quickly. This is the this will be dealt with the Maxwell-Boltzmann distribution law of speeds. Maxwell-Boltzmann distribution in the coordinate space, this tells how the particle will be, how the diffusive property of the particles, which is in the coordinate space. Okay. So, now let me start it. One can evaluate approximately this del u by del r times del u by del r and its average. These things somebody can evaluate approximately using the Maxwell-Boltzmann law, according to which number of molecules per unit volume in the region of the potential energy u r is given by n of r, means subscript r means it is a function of r, n of r equal to n naught, where at r equal to 0, e to the power minus u r by k t. That we have already derived in my last lecture in the Maxwell-Boltzmann distribution of speeds, where n naught is the number density in the region where potential energy is 0, where u of r is 0. Okay. Let us first calculate the contribution of one molecule. The average number of other molecules lying between r and r plus dr from this molecule is n r 4 pi r square dr, and hence the contribution of one molecule to r u prime r means r del u by del r arising due to all other molecule in the spherical shell of radii r and r plus dr is 4 pi n r u prime r r q dr, which is, if 4 pi n naught, just you substitute n of r. So, 4 pi n naught exponential minus u r by k t u prime r r q dr. So, then the contribution of n molecules of the gas is, if you will take summed over r del u by del r and its average equal to n by 2 0 to infinity 4 pi n naught exponential minus u r by k t u prime r r q dr. 2 takes into account the overcounting. Okay. So, we have divided this expression by 2 to avoid the duplication of every pair of molecules. Achha. When n is large and putting n naught equal to n by v, which is nothing but the density, then equation 14 gives, that means that equation of state is P v equal to n k t minus 2 pi by 3 n square by v, just you substitute n naught, which is nothing but the n by v. There is another n outside of this integration, that gives you the n square. So, P v equal to n k t minus 2 pi by 3 n square by v 0 to infinity e to the power minus u r by k t u prime r r q dr. So, if you will integrate it by parts, so this equation can be written in a simplified form P v equal to n k t plus 2 pi n square by v k t 0 to infinity 1 minus e to the power minus u r by k t r square dr. If you will assume u r tends to 0 when r tends to infinity, obviously I should assume it, because we know whenever in the ideal gas approximation people used to take why there are no interaction potential between the molecules. Reason is that, idea behind that assumptions is that, since the separation distance between the molecules is far larger than the range of the interaction. So, that is the reason there is no interaction potential. So, obviously, if you will take r tends to infinity, so u r tends to 0. So, according to van der Waals, the molecules are assumed to be hard sphere of diameter sigma and attract each other with a weak force, which rapidly decreases as the distance increases. That means, he has taken some potential energy form. So, whenever two atoms or molecules close together, they will stick to whenever they touch each other, they experiencing huge potential. Whenever their separation distance is very large, they are not feeling any interaction due to other. So, he has taken some kind of form of this potential, which is below, which is given as u r equal to infinity when r tends to sigma. It takes some finite interaction u 0 of r when r greater than sigma. If r is much greater than sigma, then it will be 0. So, if you will plug in this kind of potential energy form in the above expression 18. So, what you will get it? You will get P v equal to n k t plus 2 pi n square by v k t. Then you split this integration into two form. 0 to infinity you can make it into two forms, 0 to sigma and sigma to infinity. So, 0 to sigma, you know, this is u of r equal to infinity. So, e to the power minus infinity, e to the power minus infinity is 0. So, only 1 will survive. So, r square dr. So, that is the reason first term of this integration reduces to 0 to sigma r square dr. Second part is sigma to infinity, where it will take the form u 0 of r. Just you see this form u 0 r. Then sigma to infinity 1 minus e to the power minus u 0 r by k t r square dr. So, finally, you will do this integration. So, n k t plus 2 pi n square by v k t 1/3 sigma q plus 1 by k t sigma to infinity u 0 r r square dr. So, let us take let us say b equal to 2 pi by 3 n sigma q, and let us take let us take a equal to minus 2 pi n square 0 to infinity u 0 r r square dr. Then the above equation will be reduced in the form in terms of a and b is P v equal to r t plus r t by v into b minus a by r t, where a and b are the van der Waals constant. So, equation 20 can be written in the form P equal to r t 1 plus b by v minus a by v square. So, which is r t, if you will 1 plus b by v, if you will bring it to the denominator when b is much smaller than capital V. So, r t by v minus b minus a by v square. If you will bring a by v square on the left hand side, so you will get p plus a by v square into v minus b equal to r t, which is nothing but the famous van der Waals equation of state. So, finally, we have derived van der Waals equation of state from the more fundamental description of the atoms and molecules which constitute a system. So, that is the beauty through which is one kind of first principle calculation in the physics, which brings this van der Waals equation of state, although it was derived it very heuristically by incorporating the salient feature of the real gases. But anyway, we are able to derive a form of van der Waals equation of state from the Virial's theorem, which is theoretically correct up to term 1 by v, because if you will see it, we have terminated the series 1 by v q etcetera term. So, that is the reason this equation is theoretically correct up to term 1 by v. It is more correct to use equation 20 instead of 22, but due to its form of simplicity, this form of equation is more frequently used. So, just for the sake of completeness, if you want to write down the van der Waals equation of state for n moles of gas, then you substitute small v equal to capital V by n. So, we will get p plus n square a by v square into v minus n b equal to n r t.